Welcome to this video in which I talk to you about functions. So, first of all, why do we study functions in this course? We have uh, two main aims. The first one is um, the utility of functions in proving equality of um, sets in terms of cardinality or size. Why this is not that useful for finite sets, because we can just count them, but it's a very useful property for infinite sets, or to prove something about a set that we have, about that it is rather infinite as the set of integers, or as infinite as the set of real numbers. So typically we use a one-to-one mapping that maps every element in the first set to the second one. This means that the two sets must have the same size, because every element here has a corresponding element there and vice versa. Okay, so the second property, this will be the topic of next chapter, and later on we will also use functions to talk about the complexity of algorithms. Okay, so when it comes to the time complexity of algorithms, we will need to reason about this in terms of number of executed instructions given a certain input of size n. So it would be a certain function of that size n. Okay. Of course, you already know about functions from high school, but we need to review certain terminology to agree on a certain keywords and properties, so that you can also prove properties about functions using what we learned so far in terms of logic and proofs. So what is a function? We use this notation usually f colon a arrows b to talk about a mapping of elements from A to elements in B. This mapping, for it to be a function, it should map or assign to each element in A, every element in A, exactly one element in B. Okay, so if you have a certain mapping and you are using bubbles and arrows to represent this mapping, you should look at this side here, okay, to check whether it's a function or not at the first place. So you should verify that actually every element in the domain of the function in the set A has exactly one outgoing arrow. Okay, so and no elements in A are left blank, let's say left without any outgoing arrow. So we cannot accept a bubble here without any outgoing arrow. Okay, every element should be engaged in a certain relationship with elements from the set on the right hand side, called the codomain, B in this case, and one and exactly one relation, at most one relation and at least one relation. It means exactly one relationship. Okay, so the function f being applied to a certain element in A can be represented in this way, f of A. Okay, and this is typically equal to a certain element B in the codomain called B. Okay, so we write f of A equal to B if B is the unique element of B that is assigned by the function f to the element A of A. Okay, so we can kind of write this. So for every A belonging to capital A, there exists one and exactly one element in B, okay, such that f of A is equal to B. Okay, so it's exactly one element from the set B. Okay, and you know, like, although we didn't learn about this operator, we just evoked on during the class, we know that we can express it as there exists an element, and for every other element, b prime. If f of b prime, f of a is equal to b prime, then necessarily b is equal to b prime. Okay, so we can represent in this way, such that f of a is equal to b, and for every b prime, if f of a is equal to b prime, then necessarily b is equal to b prime. So we cannot find any other element that is equal to the image of a to f of a. Okay. Okay, good. So actually, we can see this mapping as a subset of the set A cross B. It's a subset of the set of pairs of elements, where the first one is an element in A and the second one is an element of B. So actually, we can see it as the set of A pairs of elements A, f of A, okay, such that A belongs to the set A. In other terms, it's also equal to the set of elements of the form AB, such that A belongs to A, B belongs to B, and B is equal to the image of A to f of A. Okay, so we can see it in this way. And of course, this is a subset of A cross B. Okay, so it's a very special subset where every element in the pair, every first element in the pair belongs to A. The number of pairs is equal to the size of A because every element in A appears in the relationship. And actually, the first element in each pair is different, okay, because we want for every element of A to be engaged in a certain relationship with an element from B exactly once. Good. So let's fix the terminology that we're going to use. So we say that F maps A to B, or it's a mapping from A to B. A is called the domain, B is called the codomain of F. And if f of A is equal to B, then in this case, we say that B is the image of A under F, and dually, A is the pre-image of B by F. The range of F is the subset of B that contains all the images of points in A. So it's practically denoted F of A. This must necessarily be a subset of B or equal to B. So because the F of every element in A is an element of B. So every element in F of A is an element of B. Two functions are called equal if they have the same domain, the same codomain, and they map each element of the domain to the same element of the codomain, very obviously. Okay, so good to know. Let's consider a couple of examples. So if you consider the mapping of every flag of a certain country to the main currency in that country, typically we will have one image for each element of the set on the left-hand side. So if you zoom in here, okay, you will see only one outgoing arrow from every element here. So I think this is a very good candidate mapping to be candidate for to become a function. If you consider the inverse of this function, well, actually, if you should look now at the right-hand side, okay? So the domain is, in this case, the right-hand side, and the codomain is on the left-hand side, okay? So we can easily notice that certain elements have more than one image, okay? So for example, this one has 3, this one has 2, but at least one of those occurrences are sufficient to say that this is not a function. Good. What if we group these countries? Well, actually, this case, if you consider the kind of the power set of all the the set of all the countries. Well, in this case, actually, the mapping to elements in this power set is a function, because every element here now has only one outgoing arrow, exactly one outgoing arrow. Perfect. So how to represent functions? So we either list explicitly all the occurrences, or we can define it with a certain statement, or better, we can use formulas, arithmetic formulas, or other forms. And by the way, even a computer program is actually a function. Well, this one particularly maybe um, is negotiable, because how can you define the square root function? Just think about it. Pause the video. Okay. So actually, you would write that sqrt as a function that maps every integer n, okay, to a certain value that is called sqrt of n. And this value can be an element in the, it's a double, so it's a double precision number, so it's an element of the set of real numbers, okay? Nevertheless, this requires a bit of fine tuning, okay? So it's true that we write it this way, but we all know that this number n must be an unsigned integer, okay? Because if n is equal to -1, for example, sqrt will give you an exception, okay? So I think it would have been better to define it as to define the input being an unsigned integer means an element of z plus. So in this case, yes, it is a function, because all the elements in z plus can have an image by sqrt in R, okay? But if you consider z, the entire set of integers, then all the negative integers that belong to it, they cannot have pre-images. And in this case, it's not a function, because there exist some elements that do not have any image in R. And when you restrict it to Z plus, by the way, that image is unique. Okay, so the square root of 4, for example, is 2. The square root of 2, it's something 1.4 something. So it's unique. Okay, we know that this mathematically it's unique. I advise you to go to the slides, go to the presenter mode. I mean, like project the slide on your screen, because you have an animation and the answers are revealed gradually for you. So go ahead, read the questions, answer them on paper, and check your answers. I'm quite sure that you will be able to easily answer all these questions on your own. So maybe one comment about the last question here. So what is the pre-image or pre-images of Z? So well, actually, as you may see, Z has 3 different incoming arrows. So it means that that has 3 different pre-images. So in this case, the set of pre-images of Z is ACD. So you notice that we are denoting it as a set, exactly as denoting the set of images of all the elements in A. So we also use a set notation. Well, sometimes instead of talking about f of A in the entire domain, we may talk about the function of the image of a certain subset S from the set A. Okay, so in this case, S is a subset of A. And how to define the set of images of the set S? Well, actually, by considering the set of all the images of all the elements in S. Okay, so for example, the F of the set ABC is equal to the set Z union the set Y union the set containing Z, so which is the set containing Y and Z. Okay. And the f of the set CD is equal actually to Z only, okay? But anyway, we denote it using a set because potentially this might contain more elements. So it is this set of all the elements of all the images of the elements of S. Even if there is only one, we use a set to denote it. Good. So now that we have defined those concepts, we can actually talk about further properties of functions and further restrictions that we may have on functions, which leads to which lead actually to three types of functions. A function can be an inject found to be an injective function or an injection, so, often called a one-to-one mapping or function. A function might be found to be surjective or a often called unto function. And if it is both at the same time, then it's called a bijection. I'm quite sure that you remember these terms from high school, but let's check them once again, specifically in terms of logical definition with the quantifiers and so on and so forth. So it has nothing to do, an injective function has nothing to do with this photo, but it's said to be one-to-one or an injection. And it is the case if and only if when f of a is equal to f of b, then this implies necessarily that a is equal to b. So we can say, rewrite it in this way for every ab, if f of a is equal to f of b, then necessarily a is equal to b. Can you think about the contrapositive of this one? Okay. So we can see it as P implies Q. The contrapositive is, remember, not Q implies not P. So we can reformulate it with a totally equivalent formulation where we say that actually in case not A equal to B, it means that A is different than B. Okay, so not Q, then necessarily what? F of A must be different than f of B. Okay, so if you pick up two different elements, they must have two different images. Okay, or we can also state it in this way: if the images of two different elements, two elements happen to be equal, then those elements are the same. They cannot be different. Okay. In this case, how to visualize it. So actually, when we start talking about injective and surjective functions, we have to look at this side of the relationship, at the codomain, okay? Remember to check if it is a function, we look at the at the left-hand side, at the domain, and we check that there is exactly one outgoing arrow. But in case of the injective function, we have to make sure that at max, we have one incoming arrow. So at most, okay, for some elements, we may have no incident or incoming arrows. It's completely fine. But just in case we have an incoming arrow, then it's unique. Okay, it's unique. Otherwise, the function wouldn't be injective. Okay. Can you formulate this in terms of a certain restriction on the size of A and B? Okay, so do you notice here that since we need, so every element, for it to be a function in the first place, every element in A must have a certain image, exactly one image in B. But now we are not allowing common images. Okay, so all the images are unique, okay, for every element in A. So don't you think that you need at least as many elements in B as you have in A to accommodate all these pre-images coming from A? Okay, so how can we represent it? Think about it, and I'm quite sure that you would come up with this. The size of B must be at least equal to the size of A. It can be bigger. We can have elements that have no pre-images, but it should be at least equal to the size of B. It can be even greater. What about surjective functions? So the definition of surjective function, or called onto, are functions where for every element B in the set B, there is an element in A where f of A is equal to B. So for every element in B, there is a preimage in A. Okay, so it means that such cases like the node V here or the element V here cannot be present. Okay, once again, a surjective function is not necessarily injective. So we may allow for cases like this, but once again, we have to look at this side of the relationship. So we should find that every element in B is busy with a certain preimage from A. Okay, so every element in B has a certain preimage. Some of them can have more than one. Why not? Okay, so Z has two different preimages. Why not? It's still a surjective function because all the other elements are also busy with relationships coming from A, or simply they have preimages in A. Okay, so what can we formulate about the relationship between the size of B and the size of A when the function is surjective? Absolutely, we should have the size of B less than or equal. Okay, if you have one more element here, so to keep it busy, maybe we can redirect one of these two arrows coming from A or D to that new element U. Okay, but if you add 1/4 element, the only way to make this the function or this mapping surjective is to get for it one additional arrow coming from A. If you only have 4 elements, but you have 5 elements in B, in this case, you will violate the initial condition on the function. The function says that you only have at most, by the way, exactly one image for every element in A. So if you have 5 elements here, no way you can make it surjective. No way you can map every element in B to preimages in A unless you violate the function property. Okay, I mean by mapping two different images to the same preimage. Okay, so we cannot have a size in B that is a number of elements in B that is bigger than the number of elements in A. Okay. Yep. Good. So I think you already guess it. If the function is at the same time a surjection and an injection, then we say that the function is a bijection. And just let's recall the properties that we came up in the previous slides. So in case it is an injection, then the size of A is less than or equal than the size of B, and in case it is surjective, then it's greater than or equal. Then in this case, if it is both, then no way you can have a bijective function unless the size of A is equal to the size of B. Okay, and this is the feature that we use that stems from the nature of bijective functions that we use to reason about cardinalities of sets, okay, typically of infinite sets, to be able to, if we know that already B is infinite, and we have an intuition that this A is also infinite, it's sufficient to find a mapping, a bijective function that maps every element of A to exactly one element of B and vice versa, so that we can make sure that no way for A not to be infinite. It should be infinite because it has, you should have as many elements in A as you have in B to accommodate all those elements with a one-to-one and onto mapping. Let's consider a couple of examples and check how can we prove that a certain function is one-to-one or onto. So just a recall of the statements that, logical statements that I used at the beginning. So to show that it is a one-to-one mapping, we should prove that for every x, y, if f of x is equal to f of y, then necessarily x is equal to y. You can also use the contrapositive format, if x is different than y, then necessarily f of x is different than x of y. And to show that a function is not one-to-one, it's sufficient to find particular elements x and y that are different, yet their images are the same. Okay, so example, can you show me that if f of x is equal to the square of x, can you find two different elements, x and y, such that, so can you find x and y such that x is different than y, yet f of x is equal to f of y? So I think you have already thought about all the cases where x is equal to a negative number, let's say -1, and y is equal to its additive opposite, which is 1, okay? -1 is different than 1, yet their images are the same. Okay, so all these pairs of elements, x and -x, are counterexamples, and they show you that the function cannot be injective. Okay, so unless you restrict your domain, by the way, so instead of considering all the elements of Z, if you restrict your elements in Z plus, then actually every element has exactly one image in f of x if f of x is equal to x squared. Good. So to show that a certain function f is onto, then for any arbitrary element y in B, we should show that we can find an element x in A such that y is equal to f of x. Okay? And to show that a certain function is not onto, it's sufficient to find that a particular y has no images, pre-images, sorry, in A. Okay, so no element x in A is the pre-image of y. So for example, can you show me once again that the function f of x equal to x squared is not onto given the following domain and codomain. So suppose we restrict to Z plus, but we keep on Z being our codomain. Okay, so usually f of x equal to x squared is something like this. Okay, if this is my codomain, then actually plenty of elements in the codomain do not have any pre-image in the domain. Okay, so all the negative numbers. Okay, so -1, for example, has no pre-images in Z plus in the domain. Okay, so this function is not onto neither. So I propose that you can check those examples on those slides. They are straightforward. By the way, we already discussed this example too, so 17 and 18. So please check them, try to answer the questions, and maybe we can discuss this one together, because this function is making a certain shift of amplitude 1 for every element. So for example, it's mapping 0 to 1, it's mapping 1 to 2, okay? But don't forget that it's mapping -1 to 0 here, okay? -2 to -1 here, and so on and so forth. So due to the nature of infinity, and the definition of Z itself, the set of all integers, it's well known that any integer has a certain successor that is equal to that integer plus 1. Okay, so this image actually by definition or by convention always exists. Okay, so for every element here you can have a certain element in the codomain, and vice versa. So for every element in the codomain, you can also find a pre-image for it. So this is why it's a one-to-one mapping. There will be no overlapping. It will go to the infinite in this way and in that way. Okay, so this is why it's both, and it is a bijection. This brings us actually to talk about the inverse function. Okay, when a function is a bijection, okay, we can talk about its inverse, which is f minus 1. And in this case, this inverse exists, and it is defined as follows. F minus 1 of y for every y in B in the codomain, it's equal to certain element x in A if and only if the image of x by f is equal to that element y. Okay, so it's exactly the inverse mapping of the function f. So no inverse exists unless f is a bijection. It's obvious. You can try to discuss it once again. But sometimes we allow ourselves to conventionally talk about f minus 1 of a certain element y, even if it is not a bijection, just to denote the pre-image of y. Okay, so sometimes it's done in this exception is done in the books and so on and so forth. But if you're asked about this fact, so you should say that if the function is not a bijection at the first place, then you cannot talk about the existence of the inverse function. Here you have certain visual examples. Okay, please check them. And you have an example on specific sets. You can check them on your own. And if we get back to our example of f of x equal to x plus 1, then obviously every element in the codomain Z is mapped to actually to its predecessor, which is y minus 1. So the f minus 1 of any y in the set of integers is equal to y minus 1. Okay, perfect. If we get back to the x square function, so I think we cannot define it easily as long as we do not restrict our domains. Try to think about it and to answer the questions that you have here. One particular aspect of function is composition. So sometimes we have a function that maps elements of a certain set A to a certain set B, and another function that maps functions from elements from B or let's say a bigger set that contains B two elements in a set C. So in this case, we can talk about the composition of F with G, denoted F round G or F of G of X. Okay, so we pronounce it F of G or F composite G. So, and actually this is equal to the image by F to the image by G to the element X. Okay, so we are mapping finally the original element A to the image of its image by F. Okay, good. So let's see it with a certain example. Suppose you have these two different function mappings from those elements. So each one is a function. So each one only allows one outgoing arrow from the domain. So even if we have, let's say, multiple elements having the same image here, but since this image only have one image by F, so finally we can find that the final relationship between elements of A and C using f round G or f of G is also necessarily a function, because it would map every element in A to a certain element in C. Okay, so finally we can say that the f round G of A is equal to J. So the f round G of A is equal to J. F round G of B is equal to H, and so on and so forth. Okay, good. Couple of examples, you can check them on your own. So if f of x equal to x squared and g of x equal to 2x plus 1, well, in this case, f of g of x is equal to 2x plus 1, okay, is the first mapping of x using g, then this result must be squared if you want to apply f on it. Okay, I'm quite sure that you are used to this notation. We won't lose more time on it. You can check this example on your own. But what I can say is what's important about this part is to check actually the final property of f from g. If g is an injection, a surjection, f is injection or surjection, or if any one of them is a bijection. So you may have certain rules on the composite of f and g, the composite function. So check them. I think you have a couple of exercises in the practice set that talk about those properties. We have two additional tiny parts in this deck of slides. They consist of a review of particular functions, just to guarantee that you are familiar with them. So the first one is the floor ceiling functions, and at the end we will talk also about the case functions or piecewise functions, about the factorial and about the absolute values. So let's get back to the floor and ceiling functions. The floor function is denoted by f of x equal to the largest integer that is less than or equal to x. I really like to visualize it on a certain on the axis of real numbers. So if x is a certain element here, okay, it could be something point something else, okay. So the floor of x is the closest integer to the left, okay. The largest integer that is less than or equal to x. So if here I have a certain integer n, and this is n plus 1, okay, so clearly x is somewhere in between. It can be equal to n, okay, the floor of a certain integer is equal to itself, but it's necessarily strictly less than n plus 1, because if it was equal to n plus 1 itself, then its floor would be equal to n plus 1. Okay, so anything between n and n plus, so x can be equal to anything between n and n plus 0.9999. So okay, so no one will give you this definition, but I really want you to see it this way. Okay, so it can be n, n plus 0.5, plus 0.4, anything less than half, greater than half, up to 0.99999. Okay, it cannot be equal to n plus 1. Good. And the ceiling function denoted by this symbol here, angle brackets with only the top present. So this is the small integer that is greater than or equal to x. So well, it's actually the dual case. So if you have n and n plus 1 here, then clearly x is can be anywhere except n itself. Okay, so it can be anywhere including n plus 1, okay, but it cannot be n. So it's an open interval on the side of n. So x belongs to this interval, n plus 1 included. Okay. So in this case, actually the ceiling of x is equal to n plus 1, okay, just to be sure. So if the ceiling of x is equal to n, then you have to make a certain shift. Okay, so this is n minus 1. Okay, guys, and in this case, actually, we should change it to make it this way. In this case, x is strictly greater than strictly greater than n minus 1 and less than or equal to n. Okay. You have a couple of examples here. You can check the definitions. You can also see it in this way. The white circle denotes an open interval. The blue circle denotes a closed interval. So it's also another way to see it in this way, and you can also see it in terms of those in equation. Please verify them, and also verify those properties. Okay, so I want you to pick up a piece of paper and to check those properties, to give examples for yourself on them, because we have another uh, um, more advanced property, let's say, to prove in the following slide. Okay, so in the set of practice exercises, you have several exercises on this, but let's check how can we prove properties on the ceiling and floor functions. So if we want to prove that if x is a real number, then the floor of 2x is equal to the floor of x plus the floor of x plus half. Okay. Well, actually, I think it depends on the value of x, because if x is somewhere between two different natural numbers, okay, so x is somewhere here, it's a real number, so actually it can be anywhere between and a plus one. So suppose it's somewhere in between, so it can be written as n plus a certain epsilon value, okay, and epsilon can be anything, so epsilon can be anything between like 0 and in this case up to 1 excluded, so up to 0.99999. Okay, so but if you check the possible cases, let's say n is equal to 2 and x is equal to 2.4, okay? So if x is equal to 2.4, then 2 times x is equal to 4.8, okay? It won't exceed 5, okay? But if x is equal to 2.6, let's say, a little bit above the half, then 2 times x is equal, in this case, to 5.2. It exceeds. So you have a threshold on the 0.5 for the value of epsilon. Okay, the 2 times x change. So in this case, the floor of 2 times x would change. The floor of 2 times x in this case is equal to 4, but in this case it's equal to 5. So this is why we suppose that x is equal to a certain integer plus epsilon. This epsilon is between 0 and 1. And we consider two different cases. The case where epsilon is strictly less than half, and the case where epsilon is greater than or equal to half. Okay? And we start drawing out the conclusions. In the first case, we calculate the floor of 2x, and then separately we calculate the floor of x plus half, okay? We also know that the floor of x is equal to n, okay? And we can find that they are equal. And even in the other case, we will find that the floor of 2x and floor of x plus floor of x plus half, they are also equal. So please follow the details, and I'm quite sure that you will find a way to prove this equality. Okay, so just think about those cases and the proof will make sense for you. One particular function that is useful to remember is the factorial function, but nothing new here. Just please remember the definition. I'm quite sure that you know it already. Maybe you also programmed it in other programming courses. We will talk about it later on when we talk about recursive functions and recursive algorithms. The last thing to mention in this type of slide is the piecewise functions. Piecewise functions are functions that are defined over several different intervals. So for example here, the when f of x is equal to the absolute value of x, well, this means that f of x is equal to x itself if x is greater than or equal to 0, and minus x if x is strictly negative. Okay, so typically those functions are split into two different subfunctions on different parts of the domain. The function would behave differently based on the value of the input x. Okay, So I'm also quite sure that you are familiar with this notation. So this is why we are not going to spend a lot of time on this. And soon you will use those notations in the exercises. So we just wanted in this part to make sure that you are familiar with them. Okay. Thank you for listening and hope to see you soon.